Good morning, I'm Luca Ferrari, and now I'm going to present my research activity carried out during this year in collaboration with my tutor, Professor Luigi Rovati, and the Optical laboratory. The main topic of my research activity has been the study and the realization of an optical sensor for measuring haematic pH and PCO2, which is the partial pressure of the carbon dioxide in blood. Well, the monitoring of pH and PCO2 level is of great interest in medicine. However, nowadays there isn't a real-time measurement of these parameters in the extracorporeal circulation. So I wanted to realize a new sensor which should have been biocompatible, allowing to make a non-contact measurement, disposable, low cost, and with a nice sensitivity in the haematic range. As far as all these characteristics were concerned, I chose an optical approach using fluorescein. In this way, it's possible to use the same optical instrumentation for different patients, changing only the chemical sensing part which is in contact with the blood. Well, the fluorescein is an organic molecule which have two different emission and absorption spectrum due to an energy internal conversion. For example, for methacrylate fluorescein, there is an absorption peak at 490 nanometers in blue, and an emission peak at 520 nanometers. There are some kinds of fluorescein which have an emission spectra dependent on the acidity of the solution in contact with them. So the idea is to deploy this phenomena to realize a sensor dependent on the acidity of the solution in contact with it, evaluating the intensity of the emitted fluorescent signal. In this way, I realized a pH-sensitive polymeric matrix, entrapping the fluorescein inside a polymer. And I realized a PCO2-sensitive polymeric matrix, entrapping the fluorescein inside the polymer and covering the polymer with a thin layer of silicon so that only gases can pass through. Well, in the realization of the chemical sensing element, I've used the fluorescein methacrylate as the indicator, the hydroxyethyl methacrylate as the polymer, and the polyethylene glycol diacrylate as the cross-linker. For the PCO2 sensor, I've used a biocompatible silicon. In the slide, I reported two photos of the sensor realized. The white one is the PCO2 sensor. The color is due to the silicon. And the other one is the pH sensor, where you can see the polymer with the fluorescein entrapped in. In the slide is also reported a photo taken with an SEM microscope, and it's possible to evaluate the thickness of the polymer matrix of about 35 micrometers. Well, the design and the realization of the optical head and front-end electronics has taken into account the need of the fluorescein to be excited by a blue light, the collection of the green light emitted by the chemical sensing element, and the low signal-to-noise ratio achievable. For this purpose, the optical head has been realized placing in the same mechanical block a blue LED to excite the fluorescein and two photodiodes, one used to monitor the power emitted by the LED, and one used to collect the fluorescent signal. The mechanical block has been also provided with a hole to keep the cuvette locked in front of the interrogation light. As far as the low signal-to-noise ratio achievable is concerned, the front-end electronics has been realized using a locking technique, modulating the LED driving current and modulating the fluorescent signal collected with the same oscillating signal. Well, the developed system has been first tested on water in the laboratory, then on cow blood, and finally on in vivo measurement on pig. The fluorescent signal of the pH sensor versus time is reported in the slide. It was obtained changing the pH of the blood. In the slide, also the estimated pH versus measured one is reported. It was calculated through a linear interpolation of the experimental values. I obtained a mean error lower than 0.01 degrees of pH. Well, the fluorescent signal of the PCO2 sensor versus time is reported in this slide, And it was obtained changing the concentration of carbon dioxide both in water and in air. The sensor showed a good reproducibility and a good response time, as you can see from the graphs. Well, in conclusion, I've made a sensor for measuring Haematic pH and PCO2, and finally I've tested it on in vivo measurement. The pH sensor showed a high sensitivity and a good reproducibility. The PCO2 sensor show a dependence on the level of carbon dioxide, both in water and in air. However, its sensitivity is still to be tuned into the range of interest for Haematic PCO2. In the future, I will fully characterize the sensor, especially evaluating the temperature dependence. And moreover, I want to extend the field of application of this sensor in the food conservation processes. Here is the list of my publications. Thank you for your attention.